So now we're going to be moving on to some sections where we figure out how to use the derivative to find out some more information about a function. And so a typical problem in this section is going to say find the minimum value of the function f of x equals x squared plus 1 on the interval -1 to 2. Now some of you are probably saying we don't really need calculus for this, all we really need is a graphing calculator. So here's the graph of our function, this is just f. And what we can do is visually we can look through this and we can say, well, it looks like the minimum occurs right around there. And we could zoom in very carefully. We could say, well, right there, there looks like our minimum at 0. So we have a minimum at 0, 1. Done. Now you're completely right that with graphing calculators today, it's pretty easy to just graph this stuff, pick out minimums and maximums visually, and it's not too much work. However, the problem is that this won't work in general when you have more complicated functions. So it's possible also to make up functions that depend on several variables, and in this case, this function, we can't graph it, but using very similar techniques to what we're going to learn in this video, we'll be able to find maximums and minimums of this in later courses. Also, graphing is like using a sledgehammer to kill a fly. There are far easier ways to find the minimums and maximums of this function without having to take out a computer which is capable of processing millions of instructions per second, graphing every single point of this function and looking at it. There's better ways. So before we get started in this section, what we need to do is we need to get a couple vocab words in. So let f be a function defined on an interval containing c. We're going to say f of c is the minimum of f on that interval I if f of c is less than or equal to f of x for all x and I. It's smaller than the stuff around it, and it's going to be a maximum of the function if it's bigger than everything around it. And these are also called extreme values, extrema, and the minimum and maximum of a function are also called global or absolute extrema. So I think these are best understood with a nice picture. So again, we're going to look at the graph of fx equals x squared plus 1, but this time note that we're looking at in the open interval, -1 to 2. And so visually what we can see is right here, what we have is we have the point 0, 1, and we can see that since f of 0 is less than or equal to x squared plus 1 for any value in this interval, it really is going to be a minimum. It's lower than everything else. This function, however, it doesn't have a maximum. That is, this point over here, since it's not included in the function here at 2, is not a maximum. What we're doing is we're getting closer and closer to a maximum value, but we never quite hit it. So we don't have a maximum for this function, but we do have this minimum over here. So our only extrema is this minimum. So in the last example, we only had a minimum value. We didn't actually get a maximum value. And what the extreme value theorem here tells us is it gives us a way to figure out for sure if we're going to have both a maximum and a minimum. So we need to check two things. If our function is continuous, and we're mapping it on a closed interval, so very important, continuous and closed interval, then f will have both a maximum and a minimum value on the interval. So the idea to think about is we think about it, well, if we're going to graph ourselves a function here, and it's going to start here at a and end here at b, well, what the closed interval tells us is we have a solid dot on our function at a, and continuous tells us we're going to be winding all around here, but we're never going to break or make weird jumps in our graph. And then we have to have a solid dot there at b. So what this tells us is that it tells us somewhere in between we need to achieve our minimum value, and we need to actually hit our maximum value. And both of these are very important. You need to be both continuous and a closed interval. So what could happen, of course, is we could have a function here, and what could happen is we could still be mapping from a to b, but if we're not closed anymore, the function could wind around like this, and since this is continuous, but it's not closed, we don't actually get our maximum. Since this is an open circle up here in the corner, we don't actually hit our maximum. We still have ourselves a minimum, but no max. And as a last example, what could happen? Again, we could try to graph our function from a to b. We could try to graph it on a closed interval again, but we could end up with something like this, where again, there is no maximum value. These function values just keep going up and up and up, and they never actually hit their maximum. There's no solid point that's above all other points. And this is a function, this is not continuous, so this is why it fails. It's not going to have its maximum and minimum, not going to have both. So sometimes when we're given functions, what we'll notice is we'll quickly pick out where we have an absolute maximum up here at the top, and we'll have down here an absolute minimum. But what we'll also get is we'll also get other points that aren't quite the minimum. It's not as low as it could be, but it is sort of lower than everything around it. And what we're going to call these types of points are going to be relative minimum. So we're going to say relative minimum because relative to the stuff around it, it's kind of as low as we get. So the technical definition is that if there is an open interval containing a point C on which f of C is a maximum, then f of C is called a relative maximum. And if there's an open interval containing C on which it's a minimum, then it's a relative minimum. So this point over here again is a relative minimum because it's sort of lower than stuff around it. If we look at this point here, this is not a relative max. It is definitely bigger than the stuff to the left of it, but there's nothing to the right to compare it to. So relative minimums really need stuff on both sides to compare them to. So since there's nothing on the right, it's not bigger than anything. It's not a relative maximum. Now we should also note that up here, this absolute max is also a relative max. It is bigger than stuff on both sides, so again it gets to be relative. This absolute min is not a relative minimum. There's nothing again on both sides to compare it to. So here's another definition we want to look at. What we want to think about are these things that are going to be called critical numbers. And a critical number is going to be any value where either the derivative is 0 or where your function is not differentiable. So in this case on the left, we have 2 is going to be a critical number, because at 2 here we can see that the slope is 0. That is, the derivative at 2 is equal to 0. And in the graph on the right, we see that 1's a critical number because the derivative at 1 does not exist. Okay, it's not differentiable there. It's one of our sharp corners. So these are places that are called critical numbers. Now the reason we care about these critical numbers is because these are the only places where relative extrema can occur. That is, a relative min or relative max must be at a critical number. So the way to think about this idea is that if we're going along this curve here and we're following along, well, I can't have a relative max or min here at 1 because since my slope's positive, that means I'm still going up here. My slope is telling me my function needs to keep increasing, so there must be something bigger. So it can't really be a maximum then because there's stuff bigger going on. Whereas here, right at 0, or right at 2 rather, since my slope is 0, I know that I'm going to probably be bigger than most things around it. There isn't anything necessarily bigger around me. And as I keep going down here, I can't have any maxes here because since I'm negative, I know that stuff to the left of me is bigger than me and to the right of me is smaller, so I can't be a max or min. Now what could also happen is this can also happen at critical numbers here. So if your critical point here where the slope does not exist, this could be a max or min as well, because it's hard to say what's happening to the left or right. So let's put this all together and actually find some extrema on a closed interval. So let's go ahead and try to find the max and min of f of x equals x squared minus 2x on the interval 0, 4, and we're going to try to do this without looking at the graph. So the first thing we want to note is that by the extreme value theorem, which I'm going to abbreviate EVT, extreme value theorem, we know that we have a max and min. We can be very confident that we're going to have both of these things. So the first thing we need to recall is we need to think, well, where could these maxes and mins occur? And remember that maximums and minimums could occur at these critical points. So what we want to do is we want to find our critical numbers on this interval a to b, and in this case our interval will be 0 to 4. So the first thing we need to do is we need to take the derivative of our function, and by a simple application of the power rule it's going to be 2x minus 2. And we know critical numbers are going to occur where our derivative is equal to 0 or where our derivative does not exist. Now in this case, the does not exist one is easy. We can put any number in here, so we're not going to get any of these does not exist places. But we are going to get one answer here, that x does have a critical number at 1. So the next step is to evaluate our function at any of these critical numbers and our endpoints. So what I like to do is I like to make a little table. And so what I'll do is I'll make my table here and I'll put my endpoints in. So I've got my endpoint at 0, I've got a critical number at 1, and I've got my endpoint at 4. So these are my x values. And then I need to put these into my function. And when I put 0 in, I'll get 0. When I put 1 into my function, I will get -1. And when I put 4 into my function, I will get 8, I believe. And then what I can conclude is the least of these is my minimum, the greatest is my maximum, because I know all maximums and minimums occur at either critical points or at endpoints. So I can record this that my minimum is at 1, -1, and my maximum is at 4, 8. So that's really all there is to it, to finding extremum. And what's neat is we were able to do this by not having to graph it, not having to do what the computer did, which was plug in thousands of numbers into this function, draw a pretty picture. All we had to do in our case was we had to find a couple candidates, plug in 3 numbers, and then say which one's the min and the max. And it really wasn't that much more work than having to graph it. The key things to remember is that we need closed intervals, we need continuous functions, but then we're good to go finding minimums and maximums. So don't forget to post a question in class to take the quiz, and I will see you later.